Okay, a very good morning, members. Let me hope we are all doing well. A very good morning to Mr. Oscar, Petronella, Kenya, Jerry, Navuzari. Let me hope you are all doing well.
Sure, yes, we are doing well.
Okay, that's great to hear. So today we are going to continue, I think, with the osmotic pressure. We are going to look at the graphical interpretation of this freezing point depression. Then we go to osmotic pressure. Okay, so from the examples which we did yesterday, we have some other good examples down here, I think, which we didn't pass through, but I told you at least to go through them, to try go out with them and see if possible you can write them down. I don't know whether other members are seriously trying out these numbers, because really I have received only 2 people who have shared their work with me. So I'm not sure whether others are trying or not. But if you are not trying, please, you are doing a disservice to yourself. I'm telling you this, you are doing a disservice. Yes, because trust me, after studying these concepts, if you have not tried out with them, or you have not tried out those questions, it will be hard for you to try out them next time, because you feel like they are boring, but when you try them right now, you can't feel that boring state. But if you don't try them out now and think you try them some other time, trust me, you'll feel bored and you want to do a lot of them or enough of them. So it's better you try out these numbers just after the lessons. You still have the energy, when you still have the vibe, when you still have the vigor of doing these numbers. Yeah. So it's better you do that. So I've received only work for Navzari and I think Gloria. So the rest you haven't shared your work with me. Since I think even right from the other one of vapor pressure. So if you're not trying, please make sure you try. Okay, so I was saying that yesterday I passed to go through these other numbers right here, and we saw how best we can calculate them. And right from here, I think we stopped on calculation 5. It was, I think, number item 4 around there. Yeah, I think it was item 4. So the item 5, that one was also still about calculating the molecular mass of X in water and in benzene. So this question, it's not so tricky, just that you have to understand it. Right here, it was saying 0.72 grams of compound X was dissolved in 80 grams of water, and the resultant solution had a freezing point of negative 0.14 degrees Celsius. So they continue and say, when 2.9 grams of the same compound was dissolved in 1,100, in 111 grams of benzene, in 1,011 grams of benzene, the freezing point was depressed by 0.6, because we have 111 grams of benzene. The freezing point was depressed by 0.6 degrees Celsius, full stop. In a bracket, they are saying Kf for water is 1.86 degrees Celsius per mole per kilogram. And the Kf for benzene is 5.5 degrees Celsius per mole per kilogram. So now right here, we have been given the Kf of benzene as the solvent. We have been given the Kf of water also as a solvent. So in this question, we have two solvents. We have the first solvent as we have the first solvent as water. We have the second solvent as benzene. Now the solute is one, but now you are going to find out that the molecular mass of X is different, or is going to be different when that X is dissolved in water from when it is dissolved in benzene. You have two solvents, you have benzene and you have water. Now you are dissolving it in water, at the same time you're also dissolving it in benzene. So when you come to determine the molecular mass of X in water, will be different from the molecular mass of X in benzene. So now we are going to see that how to calculate that molecular mass, or how we can calculate molecular mass. First review number 1 in the activity on page 456. 456. What is there on 456? Anyway, we'll talk about that, but that's where we are going. On page 456, we are going to reach there. It's very okay. So I was still explaining this one that we are supposed to determine the molecular mass of X in benzene and in water, but the procedures are the same, the way we have been following them. We have been given the mass of compound X, we have been given the mass of the solvent, that's for water, then they also gave us the freezing point. Then through the mass of the compound, when 2.9 grams of the same compound, that is X, dissolved in one, so still we have been given the mass of X, which was dissolved in 111 grams of benzene. And still, they said that the freezing point was depressed by, which means they have given us the DTF direct. Here, they just say the resultant solution had a freezing point, which means this negative 0 point something is not DTF. It's just the freezing point of the solution, which means you have to find the DTF here. But here, the DTF has been given to you direct as 0.6, because they have said that when 2.9 grams of the same compound was dissolved in 111 grams of benzene, the freezing point was depressed by 0.6, which means this is DTF direct. But here they said when 0.72 grams of compound X was dissolved in 80 grams of water, the resultant solution had a freezing point of negative 0.14. So that means here you have the freezing point, but because we know you have the freezing point of the solution, but because we can get the freezing point of water or pure water, we can easily get our DTF. So we are going to start with calculating molecular mass of X in water. So because we're going to start with calculating molecular mass of X in water, we are going to use the grams of water, which are 80, as the solvent. So we are going to say 80 grams of water Dissolve how many grams of X? 0.72. What about 1,000? Dissolve how many? 9 grams of X. So from here we get DTF. How do we get DTF? We are going to get TF naught of the solvent. Our solvent is water, and the freezing point of water is 0. So we are going to get our 0 minus TF of the solution. TF of the solution is this negative 0.14. So we are going to get our 0 minus 0.1 for this statement here. So TF of the solvent, then minus TF. So TF not of the solvent minus TF of the solution. So we are going to get our DTF, or our depression in freezing point, as 0.14. So this 0.14 is the one which is caused by these 9 grams. Remember, what we need is molecular mass. So remember, we have Kf. Right here, Kf for water. Our Kf for water is 1.86. So, and we said yesterday that Kf is that's what we call the cryoscopic constant. This cryoscopic constant, we said it is the depression in the freezing point, which is caused when 1 mole of a non-volatile solute is dissolved in 1,000 grams of water. Sorry, in 1,000 grams of a pure solvent. So right here, we are going to know, or we already know, that Kf is going to give us the molecular mass, because since it is 1 mole, that 1 mole is also in the molecular mass, as we have been talking about it yesterday. So we will say that this is 0.14, the DTF, or the freezing point depression we have got, is caused by these 9 grams. What about the Kf, which is 1.86, is caused by how many grams? Grams we get there, it is what we are going to call our molecular mass. So we are going to see that the molecular mass of X in water is 119. Now when you go to benzene, our benzene is right here. So you're going to see that in benzene, they said 2.9 grams of the same compound was dissolved in 111 grams of benzene. So that means 111 grams of benzene dissolve 2.9 grams of X. What about 1,000? So we get 26.102 grams of X. So in this question, we are already given DTF. We don't need to find it because the question said I was dissolved in 111 grams of benzene. The freezing point was depressed by 0.6. So since the freezing point was depressed by 0.6, that is a clear indication that our DTF is 0.6. So we already have the freezing point depression, which is 0.6 right here. And we know this freezing point depression is basically caused by these grams which we have got in 1,000. So we are going to say 0.6 degrees Celsius, that depression freezing point, is caused by 26.126 grams. What about the Kf? The Kf of benzene. Kf of benzene was given to us 5.5. So we come back here and we say, what about the 5.5 degrees Celsius, the depression freezing point? That one is caused by. So what we get here is the molecular mass, because Kf is in 1 mole, and we know molecular mass contains also 1 mole. So now you are going to see that the molecular mass you have got for X in benzene is twice the molecular mass you have got in water. Now, that's why the part C is saying, explain why the molecular mass of X differs in the two solvents. So before you explain, you tell us how do those molecular mass differ. So when you look at the one in benzene, the molecular mass of X in benzene is twice that in water, because the one of water is 119.57. The one in benzene is 239. So you can see that the molecular mass of X in benzene is twice. Bakita chichi. The molecular mass of Okay, the molecular mass of benzene, the molecular mass of X in benzene is twice that in what? The molecular mass of X in water. So as you can see it right here, here you have 239, then here you have 119.7. So you can really see that the one in water, so the one in benzene is twice that in water. But now they are saying explain, why do you think the molecular mass of X in benzene is twice that in water? So this one takes you back to association. So that this is a clear indication that this solute X associate in benzene. Because you remember what we said, that when the number of particles in the solution reduce, what happens? When the number, because we said vapor pressure lowering of the vapor pressure above the liquid depends on the number of solute particles. When the number of solute particles in the solution are many, of course, you are going to lower the vapor pressure. So the extent of lowering the vapor pressure will increase, and that will mean that the molecular mass is going to decrease. But when the number of non-solid particles decrease, that means the extent of lowering vapor pressure is going to reduce. So now remember we said the P is directly proportional to number of moles. Or we said the equilibrative property depends on the number of moles of solid particles in the solution. When you increase the number of solid particles in the solution, of course, the colligative property will also be highly affected. But when you decrease, even its extent of effect will also decrease. So, and we said because these colligative properties are directly proportional to the number of moles of solid particles in the solution, the molecular mass for it is inversely proportional. When you increase the number of solid particles, you are increasing the effect on the colligative property. And when you increase the effect on the colligative property, now you are going to lower the molecular mass, because increase in number of solid particles increases effect on the colligative property, resulting into reducing the molecular mass, because molecular mass is inversely proportional to the colligative property, like a DTF, like a DTB, like a DP. So those ones, they are inversely proportional to molecular mass. When they increase, molecular mass decrease. When they decrease, molecular mass increase. So you have to use that formula and understand that the TF, the TB, and the P, those colligative properties, they are directly proportional to any number of moles, but they are inversely proportional to molecular mass. So which means when the number of moles of solid particles in the solution increase, the colligative property will also increase, but the molecular mass will decrease. When the number of solid particles in the solution decrease, the colligative property will also decrease, but the molecular mass for it will increase. So for us to have our molecular mass in water when it is 119.57, then in benzene when it is twice, that is a clear indication that this solute X associated in benzene, or it went under association in benzene, like the molecules of X associated. And when they associate, the number of solid particles reduce. And when they reduce, of course, the colligative property will reduce also. And that one will make the molecular mass to be twice the actual value. So as you can see here, the molecular mass in benzene is twice the actual value, which is 119. The molecular mass of benzene in water is this. Sorry, of X in water is this, which is the actual value. But when you look at the one in the benzene is 239. So which means this is solute when it reached in the benzene, it associated. And once it associated, the number of solute particles reduced. Reducing the number of solute particles, that one also reduced the colligative property, which is the depression in freezing point. Reducing the colligative property will now result into increase in molecular mass twice the actual value, because the colligative property is inversely proportional to molecular mass. Once the colligative property decreases, molecular mass increase. And what makes colligative property to decrease? Decrease in solute particles. And the association reduces the solute particles. So association reduces the solute particles. When the solute particles reduce, the colligative property reduce. Reducing the colligative property increases molecular mass twice the actual value. So that's why now here in benzene, the molecular mass is twice the actual value of X, because X associated in benzene are reducing the number of solute particles in the solution, resulting into a reduction in the colligative property, hence increasing the molecular mass twice its actual value. Bukenya, we are talking about association. And as I told you, I was the other time I was explaining the association. You look at these two molecular mass. This one we have obtained is in water. The molecular mass of X in water is 119. The molecular mass of X is the same compound. The molecular mass of X in benzene is 239. Here just we are using different solvents. Here we have used water, here we have used benzene. So you have dissolved X in water and the molecular mass you have obtained is 119. Here you have used the benzene and the molecular mass of X you have obtained is 239. But now, if you are to look at these two molecular mass, you think which one is the actual molecular mass of X? Is it this 239 or it is 119? In real sense, the molecular mass, if you have used water, the molecular mass of any substance is in water, it's its actual value, because if that substance doesn't undergo association or dissociation in water, it means what you are going to obtain is its actual value, or the molecular mass is going to be its actual value. So we are taking this as the actual value or as actual molar mass of X. So this one, the 239, you can easily see that this is a multiple of this 119. This means this molecular mass here, this molecular mass here, it's twice this one in water. So therefore, since it is twice the one in water, that means it is a clear indication that there is association, that X associated. You remember when we are explaining the effect of association, and I told you these questions will be asked to you. So I told you that when we are writing these things, we say, when we are defining what colligative property is, we said a colligative property is a physical property of a dilute solution, which depends on the number of non-volatile solute particles, but not the chemical nature. And we said when a colligative property, so when the number of particles in the solution increase, the colligative property increase. When the number of solute particles in the solution decrease, the colligative property also decrease. And I gave you examples. Like if you are dealing with the vapor pressure lowering, when you increase the number of solute particles, it means you are going to still, when you increase the number of solute particles in the solution, it means the extent to which you are going to affect that vapor pressure lowering will also increase. When you increase the number of solute particles, the TF will also increase. The lowering in what? Or the freezing point depression will also increase. When you increase the number of solute particles, that the TB will also increase, or the elevation boiling point will also increase. So colligative properties are directly proportional to number of particles in the solution. Now, but we said, if you look at this formula, let me take you back here. if you look at this formula where we had molecular mass for the elevation boiling point, this one, dt equals to kb, you can easily see it right here. dt equals to what? To kb, concentration over molecular mass. Or you can easily look right from here. dt is directly proportional to concentration or number of moles, but it is inversely proportional to molecular mass, which means when the concentration increase, dt will increase, or dtf will increase, or dtb will increase. But molecular mass will decrease because molecular mass for it is inversely proportional. When concentration decrease, when the concentration decreases, dt will also decrease, but molecular mass will increase. Now, what happened? We have an increase in molecular mass in benzene because the one of water was 119. The one of benzene was 239. So, which means we have an increase in molecular mass. For us to have an increase in molecular mass, it's a direct translation that the number of particles in the solution reduced. And what can reduce the number of salt particles in the solution? It's association. When two particles come together, they form one. So that means the number of particles in the solution reduced because of association. And when they associate and they become reduced in number, now the colligative property will also reduce. And that one will make the molecular mass to increase and even become twice the actual value of that compound. So Kenya, when we say that this guy associated, we are getting that evidence right from the increase in the molecular mass, because the molecular mass increased right from 119 to 239. Us have seen this increase in the molecular mass, it means for us to have molecular mass increasing and it is even twice the active value, it means there was association in benzene. And that means the number of particles reduced as a result of association. Reducing the number of particles as a result of association, that will reduce the colligative property, resulting into increase in molecular mass because the colligative property is inversely proportional to molecular mass. So, but if you find that what you have obtained in water is 119, then what you have obtained in benzene is, let me say, is 5. That means there was dissociation because the molecular mass reduced. But because here the molecular mass increased twice the actual value, there was association. But if you find, let me say, you have obtained 119 in water, but then in benzene you have 5 point something, then it means the molecular mass decreased twice the actual value. So that means there is dissociation. The particles dissociated, increasing number, increasing the colligative property, hence lowering the molecular mass. So you have to reason out that very well. Okay, so that's how you are supposed to deal with that question for those who didn't try it out. So make sure you try out such questions. So number 6 is also there. So make sure you try it out. So Bakita was saying that the number 1 on page 456. Is Bakita here? She's still off. Okay. Okay. I think she had a challenge with this number 1, but I'm seeing she's still off. She's not around. So but I'm not seeing anything hard right here. Solution containing 0.368 grams of methanoic acid and 50 grams of benzene freezes at 5.0 dat. Calculate the relative molecular mass of methanoic. Okay. Okay, yeah. I think this is the question which needed the freezing point of benzene. Yeah. Yeah. I think this is the question which needed the freezing point of benzene, but it was not given. Okay. But I think the freezing point of benzene I gave it is 5.5 degrees Celsius. But at least they were supposed to give it to you, because really not everyone knows the freezing point of benzene. Otherwise, it was supposed to be given. But for you to do it, you have to be with the freezing point of benzene right here, because they have given you the freezing point of the solution of benzene. So when you have the freezing point of benzene, you can get the DTF. You get this, you get the freezing point of benzene, which is 5.5. You take out the freezing point of the solution, which is 5.09 free, and then you get your DTF. So you just say 1,000, sorry, 50 dissolve 0.36. What about 1,000 dissolve how many grams? After getting those grams, you tell us that this DTF you have got causes that, so is caused by those grams. What about 1.86? Oh, no. I think this was really a mistake. Because in bracket, they said the Kf of water equals to 1.86, yet we are dealing with the benzene. No. Okay, this question had the challenges. Because we are dealing with the benzene, then you can't give us a Kf of water. They are supposed to give us Kf of benzene. So I think this was just a mistake in the question. It was poorly set. Because in the bracket, we are supposed to have the maybe, but still, the freezing point is very big. It can't be that of water. Anyway, so what we are supposed to change is right here. Freezing point, this Kf is not for benzene, it is for water, so it was supposed to be changed. So this is wrong. The freezing point of benzene was also supposed to be given. So anyway, this one had a lot of challenges. There are some things which were not given, and those which were given, they were also they were not correct. Okay, that one was poorly set. It was poorly set. Okay, I think now you'll try out those other questions. So maybe the graphical interpretation for freezing point, because you want to go to depression in freezing point. So you want to go to osmotic pressure. So now this graph is like even that of boiling point elevation. It doesn't differ a lot. Still from our formula right here, we can create from our formula right here, and the depression dt is directly proportional to dp, or to vapor pressure lowering, as we said. But we know vapor pressure lowering is directly proportional to concentration, but inversely proportional to molecular mass. The way we talked about it in what? In boiling point elevation, dP is directly proportional to concentration, but inversely proportional to molecular mass. So where there is a dP, we can put concentration and molecular mass. So therefore, our dt becomes directly proportional to concentration, but inversely proportional to molecular mass. If you have to remove the proportionality sign, we are going to introduce the proportionality constant. And because we are dealing with the freezing point, the proportionality constant won't be Kb now, it's going to be Kf. So therefore, our proportionality constant will be Kf. So therefore, our dt will be equal to Kf, then concentration over molecular mass. So when you look at this equation here, it's analogous to equation of a line, where dt or dtf, this one always call it dtf because sometimes you get confused because we are dealing with the freezing point. So this one is supposed to be dtf. If you are dealing with boiling point, it becomes dtb. Yes. So right here, we are having dt. So f is going to be our y-axis. Then kf is going to be our... Now, what we're going to do, we are going to extend the mr to kf such that we remain with the concentration the way it is here. So we are going to put kf, we are going to make sure that is dt equals to kf over mr times concentration. So we are going to extend this mr where there is kf, such that we say dt equals to what? dt equals to kf over molecular mass, then times concentration. So when you look at this equation here, it is analogous to equation of a line, where dt is going to be our y-axis, or dtf, where dtf is going to be our y-axis, kf over molecular mass is going to be your gradient. The way we had kb over molecular mass as our gradient, it is the same thing here. Kf over molecular mass is our gradient. Then c, concentration, to be our y-axis. So therefore, this is going to give us a straight line, which straight line passes through the origin, because we have we don't have y-intercept. Our y-intercept is 0. So it is going to pass through the origin. It is going to be a straight line with a positive gradient, because you can see kf over mr as our gradient, it is positive. So it's a positive gradient, it's a straight line, and passes via the origin. So if you want to obtain the slope, we obtain it in the same way, but that slope will be equilibrating to kf over mr. So if you want to find the molecular mass of a solute, just use the slope of that graph, equate that slope to kf over molecular mass. So hope that one is very clear. We can all plot those graphs, and after plotting, we can still come up with the molecular mass. We can all come up with the kf, whatever has been asked, because the question can ask you to plot a graph of dtf against concentration and use that graph to obtain kf or to obtain molecular mass. So you just have to be knowing how to deal with it. After getting the slope, do we still multiply by 1,000? It depends on the units given. Multiplying by 1,000 is not mandatory. You multiply by 1,000 if you are converting some units in Nabzar. But right here, it will depend. Your vapor pressures, sorry, your DTF, your what? Your either your DT, but see the DTF is just going to be in degrees. And then your concentration down here, maybe if you want to convert it from kilograms, because if it can be given to you in kilograms per cubic decimeter instead of grams per cubic decimeter, the concentration. So the multiplication of 1,000 is just converting. For example, the way you were given the other graph which had kilo Newton meters. So kilo Newton meters, to convert it to Newton meters, you have to multiply by 1,000. So that's the thing right there. So, but it is not that every slope we multiply by 1,000. No, look at the units, which does it, right here, concentration in grams per cubic decimeter. Here, degrees Celsius. There is no need of multiplying by anything. You don't need to multiply. You just calculate your slope. Normally, you equate it to Kf over mr. So multiplication is when you want to convert units, especially when they have been given to you in kilo, like a kilonewton meters, kilograms per cubic decimeter, like that, and you want to convert them back to grams per cubic decimeter or newton meter to remove that thing of kilo. Yes, but it's not that you have to multiply through by 1,000. Hope that is clear. Okay, so the graph is here. You can try it out. Concentration that was given to you, freezing point. Now, you have to be keen, by the way. When we look at this number one here, they have given you concentration, they have given you freezing point, not freezing point depression. I don't know whether that one is very clear. What you are plotting is a freezing point depression, not freezing point. So it is the same thing which we did in vapor pressure. They give you vapor pressure, you need to plot vapor pressure lowering. So some students, they rush. We have told you plot vapor pressure lowering against concentration. Plot freezing point depression against concentration. But the table or the values given to you, they are not for freezing point depression. They are just freezing points. So which means you have to go ahead and calculate the freezing point depression for each concentration, the way you are calculating the vapor pressure lowering for each concentration. Because you have to know the solvent you are dealing with. The solvent is water. The freezing point of water is 0. And where there is no solute, you can see that the freezing point is 0. So you use this because there is no solute at this point. At 0 concentration, the freezing point is 0. So which means this freezing point is for the pure solvent. And if I want to get freezing point depression, I use the freezing point of the pure solvent. I take out the freezing point of the solution. So here I get 0. Here I will come and get DTF. I do another calc here. I get 0 here. Then I come here. I get what? 0 minus 0.16. I come here. I get 0 minus 0.32. See that I get my DTFs here. Because they're the one I'm going to plot, not freezing points. The moment you plot freezing points with the concentration, you are done. So that's why I told you, you have to be keen. Which values have you been given? Have you been given a freezing point or you have been given freezing point depression? Have you been given boiling point or you have been given boiling point elevation? And what does the task say? Should you plot freezing point depression or you plot freezing point? So when you look at this task, they are saying plot a graph of freezing point depression. The word is depression, but in the table you have freezing point. Now, if for you, you just go ahead and plot freezing point, yet the task is saying freezing point depression, that is going to be 0. So always read the tasks and the data and analyze the data very well. Because no one is going to be there in the paper with you to always remind you that please check whether what you have been given is what you are going to plot. So just make sure you know that. Don't always rush. I know when you reach in the paper and you find there is a graph number, I'm very, very sure most of my students, they always want to go for that graph number, at least to get those free marks. But the problem, they rush and they still end up losing the free marks they think they can get. So always treat those graphs very clean, otherwise they also come with the tricks. And that's why I told you, the more you practice them, these things, the more you get to learn those tricks behind. But if you don't practice them, you can't still get the what? The tricks, if you don't practice them. Okay, so I think that is done, the graphical interpretation. We want to look at osmotic pressure such that by today our colligative properties are done, and tomorrow we look at another thing. So unless there is a question about freezing point depression, otherwise we are stopping it there, such that we look at osmotic pressure. Okay. So let us look at osmotic pressure also as a colligative property. Osmotic pressure, this one comes from the word osmosis. What is osmosis? We have been defining this in bios. So since O level, you have been talking about osmosis. Even in primary, you talked about osmosis. So osmosis is about movement of solvent molecules. So they are moving from a region where they are highly concentrated into a region where they are less concentrated. But they just move, or they move across a semi-permeable membrane. Now, we know that sometimes if you happen to have two sides, one side you have a solution which is highly concentrated, another side you have a dilute solution. The solvent molecules will tend to move from where there is a high solvent concentration into a region where there is a low solvent concentration. So this one, we are going to see that if at all you apply pressure, you are going to, like, if at all I'm to apply pressure, I'm going to stop the net movement of molecules. For example, if water molecules or solvent molecules have been moving from a region where they are highly concentrated to a region where they are less concentrated, and then I put pressure on the region where they are less concentrated, it means that pressure is going to force those molecules to go back to the region where they are highly concentrated. So that one is going to create a situation where there is that osmotic balance. And that osmotic balance is created by just the pressure, which is just externally exerted. So it is what you call osmotic pressure. It is that pressure which is required to stop the net movement of solvent molecules right from the two solutions. So we are saying osmotic pressure is the minimum pressure required to prevent movement of solvent molecules from a dilute solution to a more concentrated solution when the solution is separated from a pure solvent by a semi-permeable membrane. So I was trying to break it down that you have a membrane in between. One side you have a dilute solution, another side you have a concentrated solution. In a real sense, the water molecules will move from a dilute solution into a concentrated solution. But to stop or to prevent that net movement where the solvent molecules are moving from a dilute solution into a concentrated solution, if I want to stop it, I apply pressure. But where do I apply pressure? I apply pressure on the concentrated solution such that the solvent molecules that are coming from the dilute solution are prevented from coming. So that pressure I apply on the concentrated solution to prevent movement of solvent molecules from the dilute solution into the concentrated solution across the semi-permeable membrane is called osmotic pressure. So I don't know whether you are getting that clearly. So osmotic pressure is like an external pressure which you can apply on the concentrated solution to prevent solvent molecules from moving from the dilute solution into that concentrated solution such that you create that osmotic balance. So basically, osmotic pressure is the minimum pressure which is required to prevent the net movement of solvent molecules from a dilute solution into a concentrated solution across a semi-permeable membrane. So that one also comes from osmosis because the solvent molecules are moving osmotically. Now, this osmotic pressure depends on the number of solute molecules, as we said. When the solvent molecules increase, It means you need to increase the pressure. It's like when the other side of the concentrated solution is highly concentrated or has a lot of solids, it means those solids which are there, they will need a lot of pressure for them to stop the other movement of solvent molecules into that solution. But if in that concentrated solution there is little solids, you will need little pressure. So osmotic pressure increases with the increase in the number of solid particles. That means a more concentrated solution requires a lot of pressure than a less concentrated solution. So the more you increase the number of non-volatile solid particles, the more external pressure you will need to prevent that net movement of solvent molecules from the dilute solution. When you have little solids in the solution, it means you also need little pressure to prevent the net movement of solid molecules into that concentrated solution from a dilute solution. So increase in solid particles also results into increase in osmotic pressure. Decrease in solid particles will also result into decrease in osmotic pressure. That's why we say it is a colligative property which depends on the number of solute particles in the solution. When there are many, there is a lot of pressure which is required. When there are few, little pressure will be required to prevent net movement of solvent molecules from a dilute solution. So, which means the more it gets concentrated, the more external pressure you'll need to prevent the net movement of solvent molecules from the dilute solution. So now this one here is just an experiment which we basically use to determine the osmotic pressure of a solution. I'm very sure if you talked about osmotic pressure with the menstrual detail, you talked about this diagram or this experiment of osmotic pressure. So this one, it was designed by Becker and Hartley. So that's why it is called the Becker and Hartley's method. So this method involves the use of a semi-permeable membrane, and it also involves the use of a capillary tubes. It uses a piston. It uses the you need a water reservoir. We need the gunmetal casing. So the first thing you have is a gunmetal casing, but this gunmetal casing is going to be having what we call a pressure gauge, the way you see it here. Then this gunmetal casing, you are going to put there a semi-permeable membrane, this one, and then you connect that semi-permeable membrane to what you call the capillary tubes, a capillary tube on the right and a capillary tube on the left. So the capillary tube on one side will be having a water reservoir, and that water reservoir will be having a tap to allow the water to enter. Then on that steel gunmetal casing, there is a piston, and that piston is to provide that external pressure or that osmotic pressure, because you said this osmotic pressure is going to be external. It is there to prevent net movement of solvent molecules from moving from a dilute solution into a concentrated solution. Okay, you were in the war. Let me hope you won the war. Okay, so right here, you have to understand this, that in this experiment, there are two sections. Or in this gunmetal casing, this hollow gunmetal casing here, the one which looks like a pot, what? I think it looks like a pot. So that gunmetal casing, which looks like a pot, it has the two parts. It has the solvent, like it has this upper part, then it has this lower part. So the lower part is having a solution. The upper part is having a solvent. So the upper part and the lower part, they are being occupied by the solution. Then in this semi-permeable membrane, there is another environment here where you are seeing this one is a semi-permeable membrane. Then inside it, or inside here, we have a solvent, which means the solvent molecules are supposed to move from where they are via the semi-permeable membrane into the solution, which is in the gunmetal casing. So the gunmetal casing is housing a solution. The solvent is within this tube, which tube is having a semi-permeable membrane. So we expect solvent molecules to move from where they are into the solution, because the solution is concentrated. But now, what we are going to have, we are going to keep on varying the concentration of this solution, such that you also get other osmotic pressures to plot, because at each concentration, the vapor pressure the external pressure needed, the osmotic pressure will be different. When I increase the concentration of this solution, of course, the external pressure needed, the osmotic pressure will increase. When I continue increasing, the external pressure will increase. When I continue increasing, the pressure needed will increase, like that. Because when you increase the concentration, that means you need more pressure to prevent net movement of molecules from a dilute solution. So what you are going to have here, you have a solvent inside here, then here you have a solution. This solution, I said, its concentration is going to be varied. We are going to keep on increasing the concentration of that solution. And the more we increase it, the more pressure we are going to need, or the more osmotic pressure we are going to need to prevent that minimum movement of molecules or solvent molecules from this dilute solution. So what is going to happen is that we are going to say, after arranging your experiment like that, we are going to say a solution whose osmotic pressure is to be determined is put in a gunmetal casing. I said the gunmetal casing is this thing which looks like a pot. So we are going to put there the solution whose osmotic pressure is to be determined. If that solution is having a concentration of 0.2 molar, we are going to put it there. We say, okay, the solution whose osmotic pressure I want to determine is having a concentration of 0.2 molar. So we put it there in the gunmetal casing. After putting our solution in the gunmetal casing, we are going to separate this solution from the pure solvent using a cylindrical plastic tube. So this tube here, which you are seeing, we have put there our solvent. So we are going to say the solvent is put in a cylindrical plastic tube, which is separated by a semi-permeable membrane from the solution. So we are going to put our solvent in this cylindrical plastic tube. Then our solution is in the gunmetal casing. Now, after putting it there, remember we need to prevent, because the moment you put the solvent there, and this is a semi-permeable membrane, what you expect is that the solvent molecules are going to move from this cylindrical plastic tube into the solution, because it's a region of high solvent concentration, and where it is going to the region of low solvent concentration. So that's what we expect. But because we need to prevent it, or we need to prevent those solvent molecules from entering the solution, we need to apply pressure or external pressure, which you call osmotic pressure. So what we are going to do is that we are going to apply external pressure by using this piston here. Remember, the gunmetal casing is having a piston up here. So we are going to push this piston to exert a pressure on the concentrated solution. The moment we exert a pressure on the concentrated solution, we are preventing the solvent molecules from moving from the dilute solution via the semi-permeable membrane. So we are basically preventing that osmotic movement of solvent molecules the moment we apply pressure, or the moment we push the piston and we apply pressure. So after separating our solvent from the solution using a cylindrical plastic tube, we are going to apply external pressure. That external pressure is what we call the osmotic pressure, which increases with the increase in the concentration of the solution. So the external pressure you need to prevent net movement of solvent molecules from the cylindrical plastic tube into the solution when you have a solution of 0.2 molar is different from when you have a solution of 0.4 molar. That pressure will be different. Because the solution of 0.4 molar is highly concentrated, you need higher pressure than a solution of 0.2 molar, which is less concentrated. That's why we told you Increase in concentration or increase in number of moles increases osmotic pressure or increases the pressure you need to prevent the minimum movement of what? Of solvent molecules from the dilute solution. So that's why here we are saying external pressure is applied by pushing down the piston until the level of the solvent in the capillary tube is just stationary. So we are going to push this piston down until the solvent molecules in the tube are not moving. The moment you see them that they are stationary, then you stop there. It means you have prevented their movement. But when you see them when they are still coming out of the porous tube, then it means you still have to push more until when the solvent molecules from the cylindrical porous tube are stationary or are no longer moving out from that tube into the solution. So when you see that they are stationary, then the applied pressure of the solution is read directly from the pressure gauge. Remember here where there is a piston, there is a pressure gauge. The more you press, the pressure will be recorded here that you have reached this pressure, you have reached this pressure. The more you push, the pressure will be recorded that you have used this pressure. So when the solvent is stationary, now you can easily see or record, read right from the pressure gauge the pressure you have used to stop the minimum movement of solvent molecules into the solution. So you can record it right from the pressure gauge here. So when you record it, then you introduce when you record it, you remove that solution. You introduce another solution whose concentration is different, because I told you keep on varying the concentrations. Now, if this solution was 0.2 molar, now after recording the pressure you need from the pressure gauge to stop that movement of solvent molecules into the solution from a dilute solution, then you introduce another solution into the gunmetal casing. So you introduce another solution which can be of different concentration, let me say 0.4. So you also do the same. After introducing it there, you also put the solvent into the cylindrical plastic tube. After putting it there, then you push the piston, and then you push the piston until the solvent molecules in the plastic tube are stationary. Then you read from the pressure gauge, you record the pressure there, then you remove that solution again and you put another one whose concentration is different. So you're going to see that the pressure you need when the concentration has increased is also different. So you are going to keep on doing that, and you record the different concentrations with different pressures, osmotic pressures. When you do them, or when you get them, you can easily plot a graph of osmotic pressure against concentration. So that's the experiment which we can use to determine osmotic pressure at different concentrations of varying concentrations. So what you need is just to read it and practice it out. Yeah, it is a very nice experiment, very easy to understand because it deals with the movement of solvent molecules. The solvent molecules are supposed to move from the cylindrical porous tube into the solution, which is in the gunmetal casing, but they are prevented by the pressure right from the piston. That pressure is what we call osmotic pressure. The more the solution is concentrated, the more pressure you will need, or the more osmotic pressure you will need to stop the movement of solvent molecules from the cylindrical porous tube. Okay, so when you get the values of osmotic pressures and concentrations, you can plot them and use them to obtain the molecular mass of the solute. So we are going to see how we can get that. So here I have a question. Now, in most cases, for solids whose molecular mass are too big, we use osmotic pressure to determine them. But because we cannot use freezing point, we cannot use boiling point, we cannot use vapor pressure lowering. For those ones whose molecular masses are too big, for example, polymers, we cannot use boiling point elevation, we cannot use freezing point depression, we cannot use vapor pressure lowering to determine the molecular mass of polymers. Why? Because polymers, they have very big molecular masses. And you know what happens? We said in the other formula, dTf is directly proportional to concentration but inversely proportional to molecular mass. If the molecular mass is too big, then it means DTF is going to be very, very, very small. I don't know whether you are getting that concept. When the molecular mass of a compound is too big, like a dose of polymers, then it means the DTF, DTB, they are going to be very, very small. And because they are very small, they cannot easily be recorded by our common thermometers. Now, take an example. If the molecular mass is 20,000, that is the molecular mass of the polymer. So if the molecular mass is 20,000, that molecular mass is too big. And because it is too big, that is a clear indication that the DTF of that compound or that DTB of that compound is going to be very, 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 very small. Like 0.002, 0.003, 0.0, they are going to be very small. And when they are very small, they cannot be recorded by our common thermometers. Therefore, you cannot go to the laboratory and you say that you can record 0.003 on the thermometer from the thermometer. You cannot. So which means you cannot get them. The only method you can use is osmotic pressure, because for it can even record those small changes in those what? They can read those small changes in the colligative property. So that's why here they are saying osmotic pressure is a better method to determine relative molecular mass of large microscopic and microscopic methods. Like osmotic pressure is a better method to determine relative molecular masses which are big, or to determine relative molecular masses of compounds which are very big, like polymers. But elevation boiling point, depression freezing point, they are not be used. They cannot be used. Why? This is the explanation. The reason why osmotic pressure is better in determining molecular mass of those large molecules like polymers, it's because polymers have high relative molecular masses, and in dilute solution, they give a few dissolved particles. Relative molecular mass is inversely proportional to either freezing point depression or boiling point elevation. That one I've just talked about it. And we have the formula DTF is inversely proportional to molecular mass. DTB is inversely proportional to molecular mass, but they are directly proportional to the number of moles. So I have just explained that one. If you have not understood, really you need to revisit this concept. So we are saying, because these compounds, they have large molecular masses, and we know that molecular mass is inversely proportional to this elevation boiling point, the relative molecular mass is still inversely proportional to depression freezing point. Because of that, the freezing point depression or the boiling point elevations caused by these polymers in the dilute solutions are going to be very small. The DTB, DTF, they are going to be very small because the molecular mass is too big. When the molecular mass is too big, the DTF or the TB will be smaller because they are inversely proportional. And when you get the TB or the TF, and when they are very small, they cannot be measured by our ordinary thermometers. How can you use an ordinary thermometer to measure that the TB of 0.0005 degrees Celsius? You cannot. How can you use a thermometer, an ordinary thermometer, to measure a DTF of negative 0. So to measure the TF of 0.00000140? You cannot, because the thermometer only will read the two things, one decimal place. So, but what you are having is 0.000004. You cannot. So, but osmotic pressure can be used, because for it can accurately measure those small osmotic pressure values. So that's why we are saying that for the large molecular masses, compounds with large molecular masses, you cannot use the other three methods to determine the molecular mass of those large compounds, but you can use osmotic pressure as a better method, because for it, that method can accurately measure small osmotic pressures at room temperature, and you come up with your molecular mass. So when a question comes to you and say, explain why the molecular mass of, let me say, they can give you any polymer. Explain why the molecular mass of ethoxyethane cannot be used. No, let me use that. Explain why the molecular mass of let me use which polymer. Okay, they can give you any polymer, whether additional or whether condensation. But so long as they are polymer, like a starch and others, you can still explain, because polymers like a starch, what and what, they have got high molecular masses, large molecular masses. And because molecular mass is inversely proportional to freezing point elevation and the boiling point, to freezing point depression and boiling point elevation, you tell us, since the inversely proportional to them, the freezing point elevation, so the freezing point depression and the boiling point elevation values, which are obtained, they are very small, which cannot be easily recorded by ordinary thermometers. So that those methods cannot be used because the molecular masses are too big. Therefore, the other DTB, DTF are going to be very small since they are inversely proportional to molecular mass. And that one, those smaller values of DTB and DTF cannot be recorded by our ordinary thermometers. Therefore, you cannot use those methods to obtain the molecular mass of such compounds. But osmotic pressure can be used because for it can be used to determine accurately determine those smaller values of osmotic pressure. Okay, so hope that one is very clear. How can we determine molecular mass using osmotic pressure? How can we determine molecular mass using osmotic pressure? Now, this one is very easy. I'm very sure you have the formula in your book. Now, if you're determining osmotic pressure, right here, what we need to know is that we are going to use the other formula. Because I say if osmotic pressure of a solution containing m grams of a solution in v grams of a solution is measured at room temperature, the number of moles of a solute can be determined from the expression. If you remember the other formula of PV equals to NRT, it's that same formula we are going to use. However much we are going to modify it a little bit. But we are going to use that same formula, PV equals to NRT. But where there is a P, we are going to introduce pi. Pi is osmotic pressure. So we are going to use this formula here for us to determine osmotic pressure. So it is saying pi V equals to nRT, where pi is the osmotic pressure. So we have replaced P with pi to mean osmotic pressure, where V is the volume. So the way you convert those units when we are using PV equals to, it's the same way we are dealing with this one. So by that, it doesn't differ a lot. V is going to be your volume, but this volume is supposed to be in which units? Cubic meters. If at all, we are going to use R as 8.31. The same rules you have been using when we are using PV equals to NRT. This is the same thing. When you have your R when it is 8.31, of course, the pressure should be in pascals or Newton meter. the volume should be in cubic meters, then the temperature should be in Kelvin. That is all. But when you are going to use the other one of 0.0821, that one you have to change the units. But I think this one is the better one, unless when you have been told to use the other one of 0.0821. But this one, if you have to use the 8.314, we are making sure that our pressure pi, osmotic pressure, is in pascals on Newton per meter squared, volume is in cubic meter, and our T is in Kelvin. So that one is very simple, the same formula which we have been using in the other calculations. So the rest are going to be very, very easy. There's nothing hard here. So that's why I'm going to allow some members to take us through some calculations right here. Because whatever you need is in the question. You only need the formula. You only need the what? You only need the formula. Okay. So when you look at question 1, they are saying calculate the osmotic pressure of a solution. Now this one, I'm going to choose those who are going to be taking us through. So Petronella, you are taking us through this question 1. Then question 2, Bukenya will take us through. Question 3, question 3, Gloria will take us through. Then in question 4, I think Nawuzare will take us through question 4. Then, yeah, I think those are the 4 questions which are right here. Okay. So the question is very simple to say calculate the osmotic pressure of a solution containing 4.0 grams of a non-volatile solute per liter of a solution at 27 degrees Celsius. The relative molecular mass of the solute is 40. So they want osmotic pressure, which is pi. Do you know the formula? Yes, pi V equals to nRT. R is a constant. Number of moles does that N can be M over MR. So you have been given MR, you have been given M, that's mass, molecular mass. Per liter, you have been given the volume. It is in liters, you have to convert it to cubic meters. You have been given temperature as 27, you have to convert it to Kelvin, such that you find the value of pi. Okay, so the questions are very simple. Just to prepare. So Petronella, you are taking us through that item 1. Petronella, are you there? Yes.
Yes, I'm there.
Yes, kindly take us through that item 1, how we can calculate and we arrive on pi, on our value of pi.
Okay.
And the others whom have just selected, make sure you also prepare. Okay.
So calculate the osmotic pressure of a solution containing 4 grams of a non-volatile solute per liter of solution at 27 degrees. Relative molecular mass of a solid is 40. Okay, so the volume, it's not there. Okay, let's first convert the degrees to Kelvin. So from 27 degrees Celsius to Kelvin, we shall add 273. $300. So we get 300 Kelvin. R will be 8.31. Then the mass is already there. It's 4.0 grams. Teacher,
Yes.
Mr. Josh, I have a question.
Yes.
Do we need volume somewhere?
Look at the formula. Which formula are you
Yes.
going to use? When you look at the formula you're going to use, you just have to look at the formula. The formula will tell you what you need. Pi V equals to M over MR RT. That is the same formula. So do you think you don't need the volume? When you look at that formula, do you need volume or you don't need it?
I need volume.
Yes, you need the volume because the formula is saying pi V, and the V stands for volume.
I was saying the volume.
Are you sure?
I swear I'm not saying the volume.
Very well. Read the question very well.
Oh.
Read the question, don't rush. Each statement makes a meaning there. When you read the per liter, what do you understand?
So in every liter of a solution, we have 4.0 grams.
Yes, but that means the volume you're having is 1 liter, or what you can call 100 cubic centimeters, 1,000 cubic centimeters. So they have given you the volume already, that it is a liter. So just have to convert the volume to cubic meters.
Okay. So to convert it to cubic meters, we are going to multiply by 10 to the power negative 6. So that's going to be 1,000 times 10 raised to power negative 6. It will give us 1 times 10 to the power negative 3. So then we shall come here. Pi V is equals to M out of MR times RT. Okay, I'm going to just put this whole thing in a calculator. The mass for out of 40 times 8.31 times the temperature, which is 300 Kelvin, it will give us 249.3. And then we're going to divide that by the volume, which is 1 times 10 to the power negative 3. Wait, what have I done? What have I done? Jesus Christ. Okay, I've got it. So it's 249.3 out of 1 times 10 to the power negative 3. 1 times 10 power negative 3. Okay, I've got osmotic pressure as 249,300 pressures, pascals.
I've got what?
249,300.
Okay. That is okay. So the only thing you needed here is to convert or to change the units. So thank you, Petronella. Since the temperature, the pressure, it's what the osmotic pressure is what was needed. We are using our formula, which is pi V equals to nRT, which is the same as pi V equals to mass over molar mass RT, whereby our pi is not known, our volume is 1,000 cubic centimeters, or which you can call 1 liter. If you want to convert 1 liter, you just get 1 times 10 power negative 3. So 1 liter, that's 1 times 10 power negative 3. So you have converted to cubic meters. So converting liters to cubic meters, just multiply by 10 power negative 3. If you are converting cubic centimeters to cubic meters, you multiply by 10 power negative 6. But because we are moving from liters to cubic meters, we multiply by 10 power negative 3. Then our R is 8.31, and our temperature, it was 27. We are converting it to Kelvin by adding 273, which is 300. Our mass was 4.0, and our molecular mass was 40. So just bring them in the formula where there is a pi, we don't have any value there. So where there is mass is 4, R is 8.31, temperature is 300, molar mass is 40, volume is 10 power negative 3. So you just press the calculator, you get your osmotic pressure direct. So these are very simple calculations. You have been doing these calculations right from senior 5, term 1. Okay, so who's taking us through question 2?
Master, it's me.
Oh. So take us through that item 2.
First of all, a good morning to you all.
Good morning to you.
I'm gonna take you through number 2, and it goes as a solution containing 1.5% of a polymer was found to have an osmotic pressure of 3.6 exponent 10 power negative 4 atmospheres at a temperature of 25 degrees Celsius. Calculate the molecular mass of the polymer. So, as teacher told us, I'm going to first summarize whatever is given in the question. I'll start with the mass. The mass is given is the 1.5%, which means 1.5 grams. I'm seeing also the volume. The volume is given. The volume given is 100 cubic centimeters. From this percentage, since it is 100%, so the volume will be 100 cubic centimeters. So also that is the volume. I'm seeing they have given the atmospheric pressure, which is 3.6 times 10 power negative 4. What else is given? The constant, the R is the constant. The constant we all know. There are two constants, but for me, I'll go with the 8.13, the 8.31, because it is easier for me. The temperature is given is 25 degrees Celsius, but I will have to change it to Kelvin by adding the 273. After adding there, I will get 25 plus 273, getting 298. Since I have used this constant, which is 8.31, my temperature will have to be in Newton meters. So I will get this 3.6 times 10 power negative 4. I multiply it by the constant temperature, which is in Newton meters, which is 101325. Hope we are together. So again, since I'm using Newton meters, also we'll have to change this volume to meters. But here I'm seeing, due to the other percentage, I'm in 100 centimeters cubed. So I'll have to change it to meters by dividing by, let me see, 1 centimeter. 1 meter is 100 centimeters. So I have to divide by 1 million. Let me see. 1 million meters cubed. Let me see what I get. I will be getting I'll be getting 0.001 meters cubed. So after doing this, then I will go back to our formula, which states, remember we want the molecular mass. Our formula states that 5V equals to nRT, but our N is the same as mass out of molecular mass. So I'll go on substituting. Already my temperature, my osmotic pressure is 3.6 times 10 power negative 4 times the constant, which is 325. Is 235 equaling times the 0.001 equaling to, our mass is 1.5 out of mr, we don't have it, times our constant, which is 8.31, times our temperature, which is 298. Hope we are together. Then let me first calculate here, and I see what I get. When I get 3.6 times 10 power negative 4 times this constant, 325 times the volume, which is 0.001. So 0.0036477 equaling to our mass is 1.5 times our constant, which is 8.31 times that 298. Yeah? This is 3714.57 out of the MR. So our MR is equal to this, what I have gotten, divided by 0.0036477, getting my molecular mass as 1018332.1 grams. Once I'm getting
You are getting 101.
1018332.1 grams as my molecular mass.
Okay. That's okay. So the challenge here would come from the statement of 1.5% to most of the students. Thank you, Bukenya.
Welcome.
This statement here was carrying a lot of meaning, because if you did not understand the way that we are using the other statements of 1.5%, now this one is kind of different, because the other time in paper pressure lowering, we were using that statement 1.5%, and you could say 1.5, that's I think the mass of the solute, then the remaining one is the mass of the solvent. But right here, because we are in osmotic pressure, here the mass given to use the mass of the solute. But now it is not that the 98.5 is going to be the mass of the solution, or the so-called volume. No, the volume is going to be 100 still. So the mass is 1.5. So now this statement means a different thing from the other ones we have been interpreting up. So here in osmotic pressure, this statement means 1.5 grams are in 100 cubic centimeters. So not the other stuff where we have been saying that 1.5 grams are in 98.5 grams, because you subtract of that. No, because here I'm not dealing with that concept. So the volume is still 100 and our mass is 1.5. So we are having 100 cubic centimeters our volume, we are having 1.5 grams. So we just need to convert the volume to cubic meter by multiplying it through by -10 power -6. Okay. Gloria wants to share her screen. It's okay. You can share right now. We are giving you 1 minute, Gloria.
Mr. Joshua?
Yes.
Yes, but it's telling okay. The host has to first allow it still share me.
I'm not getting you. You are breaking
Teacher,
a
and
little
let me
bit.
just continue. Okay, I was saying.
Okay.
I was saying that
Yes,
it's telling me that only the host can share. It's only the host who can share, but let me just continue.
Oh, it is saying the host is
So
the
the
one who
question.
can share. Okay. It seems you don't have the right. Okay.
So the
yes. What?
pressure. I'm reading the question.
Oh, you are trying out the question, Fidia.
The osmotic pressure of, yes, I'm doing question 3. I had screenshotted the answers and I wanted to share while people are seeing, but it's okay. Let's just continue. So the osmotic pressure of an aqueous solution of a non-electrolyte containing 5.43 grams per decimeter cubed of a solution is 7.093 exponent 4 Newton meters squared per Newton meter squared at 25 degrees Celsius. Calculate freezing point. Okay, I think that was a mistake. I think the relative molecular mass. Mr. Joshua, can you please scroll?
Yes.
Yes. Well, okay, let me get a good position. So,
Anyway, you are breaking a little bit.
notice that in the question they place. Are you hearing me now?
Yeah, you are clear now.
So they've given us the mass in the question. Teacher, can you please scroll up? We are on number 3.
Yeah, I think that's fair.
I'm not seeing the question very well. Okay, now I'm seeing it. You can you're exposing the answer here. There. You can see that they've given us the mass, which is 5.34. Sorry, which is 5.43 grams. It's right there. Then the volume. Here you notice that in the question they are telling us it's 5.43 grams per decimeter. So you notice that they are giving us the volume. So the volume is in 1 decimeter. Yeah, so we are having mass as 5.43, then volume as 1 decimeter cubed. Then our osmotic pressure is also there. It is 7.093 exponent 4. Then our temperature is 25 degrees Celsius and our R is going to be 8.31. But we are going to first convert these things. We are going to convert the decimeters cubed to meters cubed, whereby in 1 meter we are going to have 10 decimeters, right? But now we are going to cube it, which means that in 1 decimeter we shall have 0.001 meter cubed, or it will be 10 to power negative 3. Now that is the volume in meters cubed. So our temperature is in degrees Celsius. We are going to convert it to Kelvin by adding 273. So it will be 298. Then I think that's all. So we are going to substitute in the formula. Pi V is equal to MRT out of RFM. We are going to make our RFM the subject. Therefore, RFM will be equal to mass out of the constant R times T. Sorry, it is going to be relative molecular mass is equal to the mass times the R times the T out of the osmotic pressure times the volume. So our relative molecular mass, to get our relative molecular mass, we shall say 5.43 times 8.31 times 298 divided by 7.093 exponent 4 times the volume, which is 0.001. So you notice that our relative molecular mass will be 189.5. Yeah, so teacher, I got 189.58.
You said 1.1.
I got 189.
189. Eh?
0.58.
Okay. Okay, thank you, Gloria, for that calculation. So the best thing right here is to know how to convert these units. If you get to know how to convert these units, it becomes very easy for you. Yeah, this question had this small mistake here, which was saying calculate the freezing point. It was not really supposed to be freezing point, but supposed to be molecular mass, because it was the only constant remaining there. Since the pressure was given, the temperature was given, the mass was given, and even the volume was given. So I think the molecular mass was the only constant which was remaining there. So you couldn't calculate freezing point because we are in osmotic pressure. So this one, if you are writing down the question, you have to remove this thing of freezing point and you write osmotic pressure. So and you write molecular mass. So right here, as she has calculated it out, the only thing which you have to understand is conversion of these units, because that's where the challenge is going to come from. The moment you fail to convert this cubic decimeter, this 1 cubic decimeter into cubic meter, that is going to be a challenge. So just have to know, if you have cubic centimeters, how do I convert them to cubic meters? Multiply through by 10 power negative 6. If I have liters or cubic decimeter, how do I convert them to cubic meters? By multiplying through by 10 power negative 3. We don't need to derive those things, but at least simply do that. If you are converting your pressure, because now that's where even the challenge comes from. People, when they are converting pressure, let me say you are moving them from atmospheres. Yeah, it is 189.58. Yeah, that's the answer. That's the answer. So we are saying that please learn how to convert these units. How do you convert atmospheres to pascals? How do you convert millimeters of mercury to pascals? So you tell us if one atmosphere has 101325 pascals, what about these atmospheres they have given me? They contain how many pascals? So just multiply through. Then if you're converting the millimeters of mercury, if you have 706 millimeters of mercury, for them they have 101325 pascals. If they have given you 740, for them they contain how many pascals? So get 740 times 101325 pascals over 760. So get to know how to convert those units such that when you come to these calculations, you don't get confused. Okay, thank you, Gloria. Again, I think we can go to item 4.
So guys, that's item 4. Teacher,
Yes.
hope you're seeing the number.
Yeah, I'm seeing it.
Yeah. So the question is, the osmotic pressure of a solution containing 1.4 grams of a polymer X per 100 cubic centimeters of a solution is 1,200 at 25 degrees Celsius. Calculate the relative molecular mass of X. So the first thing I did is to summarize what I was given in the question and convert what is needed. So we're given the mass, which is 1.4 grams, the volume, which is 100 cubic centimeters, and we have to convert them to cubic meters by multiplying by 10 power negative 6. You get 0.0001. Then our pi is 1,200. The temperature was 25 cubic centimeters, 25 degrees Celsius. We convert them to Kelvin by adding 273. So after converting all your units and summarizing what you're given, the question wants the relative molecular mass of X. So you'll first write down the formula, which is pi V being equal to nRT. And N, we know that is mass over mR. So we make mR the subject. Then we say mR is equals to mass times R times T divided by pi V. Then the remaining work, you just substitute what you're given. So we shall get the mass, which is 1.4 times 8.31. That one is a constant, times 298 then divide by 1000 times 0.001, and the MR we are getting is 28,891.1. Since they want just the molecular mass, you're not going to put the units because it's just molecular mass, not molar mass. Yeah, I have a problem of rain and I'm in a classroom. Just
Okay. So
yeah, and
thank
then
you. Hmm.
part B, I don't know that you can hear.
We can hear you now, sir.
Yeah, part B is saying determine the number of monomers in X. So the formula of get the number of monomers is molar mass of polymer divided by molar mass of monomer. The molar mass of monomer is always given, and in this case they gave us as 28. Sometimes they don't give, but then this one they've given us, which is 28. So you get the molecular mass you got up, divide by the 28, get 1031.825 monomers.
Okay.
Yeah,
I can
teacher,
see
those are
that.
the. So I'm done.
Okay, that's great. That's great. Thank you.
So can I remove?
Yeah, you can remove. Okay, so thank you, Nabuzari, for that presentation. Now we have got our molecular mass as 280,891. Yes, that's okay. And when you divide through by the 28, the monomers we are getting 103. So when we are writing the number of monomers, we don't write the points. You just write the whole number. So when you write it like 1.8, this point is not making a meaning because the monomer is supposed to be a whole number. So what you do, you just either round off or you truncate depending on the value which is after the point. Now when you look at this value 1031.8, you can easily round off and it becomes 1034. But if it was 1031.2, you just remove that and it becomes 1031. So you can look at the value which is after the point. If you can easily round off and it gives you a whole number, or if you can't, then you just truncate it. Because 0.8, that is of course almost a monomer, but 0.2, that is not a monomer, so just leave it. So otherwise, when you are writing the number of monomers, you don't give points. It's supposed to be a whole number, not a decimal number. Hope that is clear. Okay, so we have other additional questions right here, down here. You have to try them out. So if you get time, make sure you try out all those other questions. Try out those other questions. The ones of osmotic pressure, they are right here. They are not hard. Just read the questions, understand them, and try them out. Otherwise, the more you try these questions out, the more you understand the concept. So, in your free time, kindly pull out these questions and try out them. But still, osmotic pressure has a graph, the way we have seen the graphical interpretations of other qualitative properties. But even osmotic pressure has got a graph. Right from the equation we know, which is pi V over N RT, we can still modify it a little bit, and it becomes pi equals to RT over mRC. The volume, remember, if this concentration is got by getting mass over volume. Mass over volume gives us concentration. That's why we have a C here. This concentration, it is coming from the mass, which was up here. Then the volume, which was on the other side of the pi, it was divided by this mass here. So mass over the volume from this side give us concentration. It is even here in the bracket. Mass over volume equals to concentration. So what remain with is pi equaling to RT over molecular mass times concentration. So this equation will also resemble or will be analogous to equation of a line. And therefore we can get our graph right from there for osmotic pressure. So our pi will be the pressure, which is going to be plotted on the y-axis. Then RT over molecular mass is going to be our slope. Then concentration, which concentration we have got from mass over volume, is going to be on our x-axis. So yeah, that's how we can get the graph, or we can using osmotic pressure or for osmotic pressure. So for that case, still the graph is going to be having or to be passing through the origin because the y-intercept is 0. It's going to be a straight line. It is analogous to equation of a line with a positive gradient. So it won't differ from the other up graphs, just that what you have to know, the slope equals to what? Here the slope equals to RT over molecular mass. For the other case of freezing point, the slope was equaling to Kf over molecular mass. For boiling point, the slope was equaling to Kb over molecular mass. For vapor pressure lowering, when we have used the concentration, you know what it was equaling to. I think it was the molecular mass of the solvent, P naught of the solvent over density, something like that. So you have to know all those what things, that if I plot a graph, they majorly want a slope. And if they want a slope, the slope will be equated to what? Molecular mass equals to this and this. So you have to know those things such that when you plot a graph, you know even how to use the slope right from that graph. Okay. So unless there is a member with a question right here before we vacate, you can easily ask the question before we call off the lesson.
Excuse me, teacher. For me,
Yes.
I don't have a question, but I have a concern. Some of us don't have the book, so I'm requesting you to kindly scroll so that we can take screenshots of the questions.
You don't have the books? Them is fine?
Flying, yeah. You've just joined.
Oh, the group, eh?
Yes.
Now, your friends have those soft copies. So either one of you should share that soft copy in the group, such that those who joined later, they can have the access. Or else I'll try to reshare. I'm going to reshare it. Okay.
Okay,
In the
teacher.
group.
Thank
you.
Teacher, excuse me, sir.
Yes, Nawza.
Teacher, I don't know whether I'm the one who didn't hear anything about this point, but then I'm confused on when to use. We have R being 8.31 and then R being 0.082. When do we use 8.31 and then when do we use 0.082?
Now, 8.31. Now, it will depend on what you want to use. It's you who decide. But when you decide, you have to follow the rules. For example, when you reach in that calculation and you say, me I'm comfortable with using 8.314 or 8.31, whether 8.31 or 8.314. If you feel you are comfortable with that, you follow the rules of that constant, that the moment you use that constant, your units of pressure should be in pascals or Newton meter, your volume should be in cubic meters, and your temperature should be in Kelvin. Simple. The moment if you have to use that constant, but if someone will say, no, I don't want to use 8.315, I want to use 0.0821. or 0.082. It can be 0.082 or 0.081. If you want to use that and if it's what you are comfortable with, you still have to follow its rules. When you are to use the 0.0821, your pressure should be in liters. Or it, is it yeah, liters, liters. Then it should be in liters. Then that's the volume, should be in liters, or cubic decimeters. Then your pressure should be in, because we use either 760 millimeters of mercury or we use atmospheres. But if you are to basically use the 0.0821, your pressure is going to be in atmospheres. And then your volume is going to be in liters or cubic decimeters. Temperature is going to be in Kelvin. So you have to follow the rules. So that is it. So when to use it, when you feel you want. If you want to use 8.314, it is okay. But make sure you follow the rules. Convert the units basing on the constant you are going to use. If you are going to use 0.0821 and if it is the one you are comfortable with, follow its rules. That if I use this, my pressure should be in atmospheres and my volume should be in liters. If I use the other one, my pressure should be in pascals or Newton meters, and then my volume should be in cubic meters. So you can
So guys, hope you're getting. I think today's
okay. I think you're going to stop here. If at all there is no any more other question. So we meet tomorrow. I think tomorrow we'll be talking about some organic chemistry. So we talk about carbonyl compounds. We are going to introduce carbonyl compounds. So those who attend the holiday session will benefit from them. If you come back, at least you come back when at least for your head, you know some other concepts in other organisms. So look at those carbonyl compounds. Yeah, I think it will be better either look at carbonyl compounds or applied. I think. Anyway, but I think you look at carbonyl compound, that would be kind of better. Okay, so I think we stop here. Thank you for attending. We meet tomorrow.